Okay, here we go with filtration and reabsorption. And we're just going to start right off with the equation for filtration and reabsorption, which is the net filtration pressure. If the answer for the net filtration pressure is greater than 0, then you end up with filtration happening, so things moving from the blood into the tissue. If the answer is a negative number, so less than 0, that means that you're having reabsorption, so things moving from the interstitial fluid back into the blood. So how we figure this out is two factors, which then each of those factors are going to be able to be divided into two of their own factors, so we have a total of 4 things that we need to think about. So for net filtration pressure, or NFP, we would find the net hydrostatic pressure, or NHP, and we subtract from it the net colloid osmotic pressure, or NCOP. The net hydrostatic pressure is a comparison of the blood pressure inside the capillary versus the pressure of the interstitial fluid pushing back on the capillary. The net colloid osmotic pressure has to do with proteins that are dissolved in the fluid, such as blood or interstitial fluid, and this is an attractive force for water and solutes. So we would be comparing the proteins in the blood that are attracting water and solutes, trying to keep those things in the blood, versus any proteins that may have made it out into the interstitial fluid, which would be attempting to attract water and solutes into the interstitial fluid. So if we have a case where we have a continuous capillary, we're not going to really have those proteins out in the interstitial fluid, but if we had a sinus-like capillary, we would have plenty of those proteins in the interstitial fluid. So let's take apart each one of these, the net hydrostatic pressure and then the net colloid osmotic pressure, and do each one of those individually. So the net hydrostatic pressure is the capillary hydrostatic pressure, or CHP. This is just the blood pressure inside the capillary. This is going to work on pushing things out of the blood vessel, working towards increasing filtration. And then we have the interstitial hydrostatic pressure, which is the pressure of the interstitial fluid. This is going to be pretty low, 0 to 2 millimeters of mercury-ish. It's not really a very high pressure, but it will be pushing back against the capillary, working to decrease filtration. Now for this one, the net colloid osmotic pressure, we're going to take the blood colloid osmotic pressure, or the BCOP. That's the proteins that are in the blood that are trying to keep water and solutes in the blood. And then we'll subtract from it any proteins that might be in the interstitial fluid, so the interstitial colloid osmotic pressure. So if we look at this equation, the net filtration pressure equals CHP minus IHP minus BCOP minus ICOP. So the net hydrostatic pressure minus the net colloid osmotic pressure. If you just think of this mathematically, and I know nobody likes to think of things mathematically, but it's not that intense of math. Just think, the higher this number, the more filtration you have. And this is the thing that you're subtracting things from. So the higher this number is, the higher your net filtration pressure is going to tend to be. So this would work towards increasing filtration, pushing things out. That capillary hydrostatic pressure is pushing things out of the blood. Now you're subtracting the interstitial hydrostatic pressure from it, so that's going to be trying to reduce that number here. So the bigger we have this number, the higher we're going to have the net filtration pressure, and this is trying to reduce it. So that would be working more towards reabsorption, working to lower filtration. But it's going to be a pretty low number, so it's not going to do a good job of that. Now, this number, the bigger this whole number is, the smaller this number will be. Because if we have a number here and we subtract a big number, that's going to just make this end answer smaller. So the higher this number is, the lower our filtration is going to be. And that makes sense if you think about what this is. It's proteins in the blood that are trying to keep water and solutes in the blood, so working against filtration. Now if we make this number bigger, it'll make this whole factor smaller. So if we had, like, let's say 10 minus 0, we get a number of 10. So let's say that's a strong number. It's not, but let's pretend. Now let's keep this at 10, and let's say this is 7. We do 10 minus 7. Now we have 3. So we're subtracting a smaller number from our whatever this happened to be, which would increase this. So this number is working more towards reabsorption. And this will be, if we're talking about a continuous capillary, which we'll do in our first example, it'll be really low, 0 to maybe 1 or 2 millimeters of mercury. But if we were talking about a sinusoid capillary or even a fenestrated capillary, this number is going to go up. So just think of things in terms of whether it's working to make this number bigger, so working for filtration, or if it's working to make this number smaller, working towards reabsorption. So this number works for filtration, and so does this one. These two numbers work towards reabsorption. So these try to lower the total net filtration pressure. These two try to increase it. Okay, so let's look at this in practical terms. Here is our capillary. Here's little proteins in there. That's representing the blood colloid osmotic pressure. So attracting water and solutes towards the blood. This is representing the interstitial colloid osmotic pressure, so any proteins in the interstitial fluid. This would be attracting water and solutes towards the interstitial fluid. So this is working for reabsorption or against filtration. This is working for filtration, trying to pull things out of the water towards the tissue. Now for the hydrostatic pressures, CHP, blood pressure inside the capillary. The higher the pressure inside the capillary, the greater the force pushing out, so working towards filtration. And then IHP, the interstitial hydrostatic pressure, pushing back, resisting filtration, working more towards reabsorption. So just like we said. So capillary hydrostatic pressure increases filtration. Interstitial colloid osmotic pressure increases filtration. Blood colloid osmotic pressure causes more reabsorption, less filtration. Interstitial hydrostatic pressure causes more reabsorption, less filtration. Now these two are going to be relatively small. These are going to be the big determinants of whether we have filtration or reabsorption in most cases. So here you can see I've just listed out what I just said. Okay, so if you want to take a screenshot of that or copy it down, but that's what we just said. And there it is, listed out for increasing filtration or things that decrease filtration. Now, just to illustrate, we've mentioned this a few times, but I just want to make sure that you are on the same page. Here's the fenestrated capillary, or if it was a sinusoid capillary, we'd have a bigger gap. Here's a protein getting out of the capillary going into the interstitial fluid and causing the interstitial colloid osmotic pressure to increase. So that would make a difference, and it can make quite a big difference in the filtration pressure. Now, let's just take an example of just a regular capillary that just has regular perfusion, and I'm going to use the same numbers that we used from our example before for the pressures of the capillary at the beginning, having a capillary hydrostatic pressure of 35 millimeters of mercury, and at the end of the capillary bed, having a capillary hydrostatic pressure of 18 millimeters of mercury. For our example here, we're going to have interstitial hydrostatic pressure be 0 and interstitial colloid osmotic pressure be 0 also, just so we can see how these two things interact, the difference between capillary hydrostatic pressure at the beginning of the capillary bed and at the end of the capillary bed, and then how that compares to the blood colloid osmotic pressure. Now, I just want to make sure that we all understand that this is just an example, and it's not going to always be that way where a capillary starts off with a high pressure and goes down to a low pressure. We might really dilate those arterioles and just have a strong flow throughout this entire capillary bed, and have this flow not really decrease at all. It might be like, just say 34 or 33 at the end of the capillary bed. Or we might have constricted it so much that the decrease isn't going to be really that noticeable. Maybe it's like 5 millimeters of mercury here, and then it's like 3 millimeters of mercury here. So it can vary, but this is just an example of one particular situation that we can have. Now, for blood colloid osmotic pressure, a typical number for that is about 25 millimeters of mercury, and this will depend on each person and what you've ingested for the day, all sorts of things. So this will vary a little bit, but it's not going to vary from 1 second to the next in the capillary bed. So let's do the situation running through the equation at the beginning of the capillary bed, and then we'll run through the situation at the end of the capillary bed, and we'll compare. So the net filtration pressure, here's the equation: capillary hydrostatic pressure minus interstitial hydrostatic pressure minus blood osmotic pressure minus interstitial osmotic pressure. And when we plug in this number, 35 minus 0, because we're going to see some 0 for those, and then minus 25, that's the blood osmotic pressure, minus 0. It's essentially just a comparison, because we've set these to 0. It's just a comparison of capillary hydrostatic pressure and blood osmotic pressure. 35 minus 25. That gives us 10. That's filtration. So that's a nice strong filtration number. If we do it at the end of the capillary bed here, capillary hydrostatic pressure is 18. Blood osmotic pressure stays the same. All of these things stay the same. We have them set to 0. Now we get 18 minus 25. That's negative 7. That's reabsorption. So in this situation, we have filtration happening at the beginning. It's getting less and less and less as we go through, and then it starts to reverse and turns into reabsorption, which gets stronger and stronger as the hydrostatic pressure changes. So I'm going to ask a question. I'll give you like a second to think about it before I just drop the answer on you. But if we held these at 0, so just essentially ignoring these two, what capillary hydrostatic pressure would give you a net filtration pressure of 0? Give me a second. So the answer to that is 25. If capillary hydrostatic pressure is 25, and then blood osmotic pressure is 25, that gives you a net filtration pressure of 0, and that's where you'll make the switch from filtration to reabsorption, wherever that might be on this capillary bed. Okay. Now, of course, interstitial hydrostatic pressure and interstitial osmotic pressure will probably be more like 1 or 2-ish, or more if we have a fenestrated or sinusoid capillary. So they will alter this factor just a little bit, but not that much. The main players are capillary hydrostatic pressure and blood osmotic pressure. Okay, so in case that wasn't enough fun for you, let's make that equation a little bit more fun. So here's our equation. Ignore the KF and ignore the little squiggly thing for a second. This is the equation that you know and love by now. Okay, it's the same exact equation. Now we're going to add this KF in front of the net hydrostatic pressure, so it's going to alter what happens with the net hydrostatic pressure. And then we're going to add this little squiggly thing, which is going to be affecting the net osmotic pressure. So what is the KF? It's the filtration coefficient. This has to do with how permeable the capillary bed is, how easy it is for filtration to occur in this capillary bed. So it has very much to do with the surface area of the capillary bed. The greater the surface area, the greater the filtration coefficient will be. And the bigger this number, the bigger the net hydrostatic pressure will tend to be, which means that you'll have a higher net filtration. So let's just think if we had just our regular equation and we had, let's say 35 and this was 25, and without these two numbers in here, we would end up with a net filtration pressure of 10, say, because we're just set these to 0 to make life easy. But then let's make this 2. Let's make a filtration coefficient of 2. So now we would have 25. Let's just write that out. That's just easier. So 2 times 35 minus 0 minus 25 minus 0. So that would be 70 minus 25, which gives us, oh lordy, 45. That just made a ginormous difference in the net filtration pressure because we multiplied this by 2. Now if we made it small, if we did it by half, so 0.5 times 35 minus 0 minus 25 minus 0. So that would be 17.5 minus 25, which would give us, sorry, 7.5, negative 7.5. I'm sorry if my math skills are not up to par. But you get the idea. It's a lot less. Now it took us all the way into reabsorption. So it makes a big difference is what I'm trying to say with my clumsy math here. So if you increase the filtration coefficient, you increase the net filtration pressure. If you decrease it, you decrease the net filtration pressure. Now this thing over here is called the reflection coefficient, and it has to do with how permeable the capillary is to proteins. And this is all really having to do with whether the capillary is a continuous capillary, or if it's fenestrated, or if it's a sinusoid capillary. Now if it's a low number, if it's a 0, that means it's a sinusoid capillary. Lots of proteins getting out, so your interstitial osmotic pressure would be going up as this is really going down, making 0. So this is being a higher number, and this is going to be a lower number. If it's fenestrated, it's going to be somewhere between 0 and 0.5, and the more fenestrations it has, the lower the number. And then a continuous capillary would be 1. So it just ranges from 0 to 1. The lower the number, the bigger the holes. The higher the number, the smaller the holes. So let's just kind of plug that in to our equation. Let's just set this at 0. Let's ignore the fact that when you have a sinusoid or fenestrated capillary that's going to go up. Let's just ignore that so we can just look at the math here. So we'll also ignore the filtration coefficient. So we'll do 35 minus 0, and let's just do a continuous capillary. So we'll make that reflection coefficient 1, and that's 25 minus 0. So when we do that, it hasn't changed anything at all, so we just get 10, just like we did before. Now let's make it 0. Let's just be extreme about it. So 35 minus 0, like before. Now we have 0 times, and now it doesn't matter what the heck numbers we're putting in here, because when you do, multiply by 0, it makes this whole thing 0. So 35 minus 0 is 35. So the lower this reflection coefficient went, the higher the net filtration pressure goes. Okay, so be able to think of these numbers in those terms. If I say on the test, you have a really high reflection coefficient, or you have a really low reflection coefficient, what happens to your net filtration pressure? Or with any of these terms. And you can always do what we did, just plug in made up numbers and see, did it go up or did it go down? You can always do that on the test. Just make up your own numbers if it helps you to do that. Now this here, this is just another way of showing this, and if you go into any sort of physiological research, this would be more how this equation would be showed. I like this form of the equation better. I think it's more just easier to look at, but just so that you are familiar that this exists, it means exactly the same thing. It's just different symbols for the same things. So JV is the net filtration pressure. There's that filtration coefficient, and then here's the net hydrostatic pressure. It's pressure in the capillary, so capillary hydrostatic pressure, minus pressure in the interstitial fluid, so interstitial hydrostatic pressure. There's our reflection coefficient, and then here's our colloid osmotic pressures. So in the capillary, so blood colloid osmotic pressure, and then in the interstitial fluid, so interstitial colloid osmotic pressure. Okay, that's the worst of things. Okay. Oh, I did the examples. I didn't have to do the math after all, because I already did it. I think I did it wrong, too. Anyway, doesn't matter. So the same math that we just did. Okay, last thing to talk about, the Bayliss effect. Oh, and when I said I did it wrong, I think I did the math wrong. It's like 2 times 35 minus 25, that's 70. Minus 25, that's 45. Yeah. Okay. So yeah, now it's all correct. Just showing the difference in the filtration coefficient and the reflection coefficient. So what we just did on the other page, but with better math. Okay. Last thing to talk about for this section is the Bayliss effect. The Bayliss effect has to do with a reflex, essentially, of if you have too much perfusion happening in a tissue, you're going to have this reflex that constricts the smooth muscle of the arteriole going into that tissue. And it works by having this high blood pressure in the vessel. Here's a smooth muscle cell, so the blood vessel would be, like maybe right there, and the pressure is too much. So that pressure opens stretch-activated sodium channels. So sodium comes into the cell, depolarizes it, and that causes an action potential in the smooth muscle cell. In smooth muscle cells, the action potentials involve L-type calcium channels. So the L-type calcium channels open, calcium goes into the cell, it binds to calmodulin and activates it. That's an enzyme inside the cell. And then calmodulin is going to activate something called a myosin light chain kinase. The myosin light chain kinase is going to work on myosin, and it's going to affect this thing called the light chain, which if you look at our myosin molecule here, we have the tail, we have the head, and we know that for any kind of contraction to happen, we need for the myosin head to bind to actin and to pivot. Now this is prevented in a relaxed state by this little kind of a lock around the neck of the myosin head, which is called the myosin light chain. So the myosin light chain kinase is going to unlock that, which enables the myosin to bind to the actin, which, because it's smooth muscle, it's not in a sarcomere, it's just in a little bundle. But if you think of, let's see if I can fit my arm in here again. So here's my arm. The arm would refer to the tail of the myosin, and my hand will be the myosin head, and it wants to bind to actin so that it can have a contraction. But it's got this myosin light chain on it, so it can't bind and pivot. But when we bring the calcium in, which activates calmodulin, which activates the myosin light chain kinase, the myosin light chain kinase takes away that myosin light chain, and the myosin head can bind and pivot. And that causes vasoconstriction and reduces perfusion. So negative feedback for if your perfusion has gone too high. Okay, and that is it. That is the end of material for exam 2. So no more stuff about blood for exam 2. We're done.